This is the final presentation for the design of an antenna mounting structure for zero-gravity crewed environments by Team NASA Mount, Sharif Chang, Zachary Keller, Jesse Reisner, and Claire Soroki. This project seeks to design an antenna mounting structure for space applications. The mounting structure often dominates any antenna installation in size, weight, cost, and schedule. The mounting structure also places the antenna at the most optimal position to avoid radio opaque structures and provide good signal range. The antenna mounting structure must also withstand astronaut kick loads and other environmental factors. Additionally, deployability in such a structure is often desired for applications where space is heavily constrained.
So the project background applications, the antenna mount system we are designing will be used to deliver Wi-Fi to devices outside of spacecrafts. The two main applications of our design include number one, the retrofit design for the International Space Station, and number two, a new design for the future Lunar Gateway missions. So for the first application, the International Space Station, this will be a retrofit design to the already existing antenna mount. The antenna must attach to a pre-existing handrail, and the handrails must not deform from the kick loads from the astronauts. The second application is the Lunar Gateway missions that set to start in 2024. There are no pre-existing attachment constraints, and the antenna structure will be attached to rigid beams. There is a possibility to explore deployable designs. However, many mission details are still classified.
Our problem statement is stated as such. The objective of this project is to propose multiple novel concepts for antenna mounting structures in a zero-gravity environment, quantify their performance using simulations, then choose the optimal design to prototype and test.
Our team developed a set of engineering requirements to help evaluate our designs. The most basic of these requirements are the physical constraints, which include the weight and antenna height of the structure. Additionally, each design must also withstand the kick loads, and these kick loads must not exert enough torque on the attachment point, whether that is the handrail or the external rails of the Lunar Gateway mission. Additionally, the designs must also function in space applications, which include being able to function in a vacuum, being able to withstand extreme temperatures and vibrations from the spacecraft. Finally, the designs must not injure astronauts in any way, either from snapping back or from any sharp features which may damage the astronaut spacesuit. 3 leading concepts were developed in order to explore different applications. One design was dedicated for the International Space Station, while the other 2 were dedicated for the Lunar Gateway mission. Additionally, one of the concept variants is deployable, while the other 2 are pre-deployed designs. Our team also explored different design aspects such as the attachment point, some having single point attachment and one design having multi-point attachment. And as the designs are meant for different applications, 2 of the designs will explore a rigid design structure, while one of them will explore a compliant design structure. Concept variant 1 is shown here, which is attached to the handrail of the ISS. Concept variant 1 consists of a lattice structure, which is meant to both reduce the overall weight of the structure and increase the compliance in order to absorb the kick loads and prevent the handrail from deforming. This design is advantageous for its lightweight, but its compliance could also be disadvantageous if it snaps back and injures astronauts, and the compliance could also be an issue due to vibrations from the spacecraft.
Concept variant 2 is seen here and is a rigid multi-point attachment that connects to the Lunar Gateway. It uses an I-beam to minimize weight while increasing the strength in its weakest direction. Some advantages it has is it offers rigidity due to its multiple attachment points and can also act as a handrail for astronauts to grab onto during spacewalks. However, some disadvantages are that it requires more material than other designs, thereby making it weigh more, as well as astronauts' limbs could get caught within the structure and they could injure themselves.
For concept variant 3, it is a deployable design that attaches to the lunar gateway. This design uses torsional springs to deploy as well as a latch to hold in place. Some of the advantages is that it is a simple design and mechanism with quick deployment, as well as the disadvantages, which it could have structural instabilities and cause harm to astronauts when deploying.
To evaluate our designs, we developed this plan, which includes 3 stages. The first stage will test all 3 concept variants in its most basic engineering requirements, which include the mass, the antenna height, and a static loading simulation, which simulates the astronaut kick load. The static simulation will also test the strength of the attachment point on both the handrail for the ISS and the external rail for the Lunar Gateway mission. Through a decision matrix, our team down selected to a single leading concept variant, which will be further tested with vibration simulations and thermal loading simulations. Finally, our team also prototyped a functional model which can be tested in person for deployment and also injury to users through a static loading test. The stage 1 simulations for concept variant 1 are shown here. Initially, there was excessive yielding in both the handrail and the structure itself, but through a series of iterative design changes, which included reducing the wall thickness of the lattice structure, we were able to reduce the yielding on both the handrail and the structure to within the yielding stress of the materials used. The structure was also moved to the side of the handrail where it is more likely to sit in an actual application.
Stage 1 simulations for concept variant 2 are seen here. On the left, there was yielding within the rail of the lunar gateway, and through an iterative process of changing the cross-sectional area of the I-beam, the simulation seen on the right was conducted where no yielding was seen anywhere on the structure.
For concept variant 3, as you can see for the first simulation that there is yielding in the hinge. For the second picture, you can see the U-bolt, which is supposed to be for the latch. This was a set point in the simulation, so you can see that there is some yielding there.
In order to decide which concept to prototype, we created a decision matrix. As seen, the criteria on the left was ranked through by their importance, and each design was scored with a score of 1 through 10. The concept variant 3 had the highest score of 180, so we decided to move forward and prototype that design.
Our prototype of the concept variant 3 is comprised of both off-the-shelf and custom parts we created. The total cost of our prototype design came out to be around $350, which is well within our $1,000 budget. The pictures below illustrate the major components used in our design. These pictures illustrate the final product of our deployable structure locked into the latch. This slide has a video that shows our structure deploying into its final upright position. In conclusion, we have developed multiple concepts. Stage 2 simulations and attaching the burn wire and latch onto our prototype are a few additional actions we need to complete, which will be discussed in the final report by December 4th.
We have included our references here for your further consideration. Thank you for your time.